class.
Yeah.
Almost straight.
He hasn't introduced me to it yet, but I know these things.
There we go.
Bring in my
Excellent.
markdown.
You text him. That's what I try to tell him all
Oh
the time.
man, we are zoomed in big time.
3 minutes away, you just text me. I'll come up here.
Yeah.
And a lot of classes, when I gave my schedule, like, well, it's gonna vary every week. If I'm here in the morning, I'm on here, or in the afternoon.
Yeah.
Just, but it's exactly like, I
I've got
could be
pages
good most of the time.
where I write what I think is important, and then I've got these
Like, it's not
functions.
that
But basically,
I'm busy and have appointments, it's like, no,
where I can just write them all down.
I'm just
They work.
not here.
YouTube's all jacked up. I think they're live again. It's like zoomed in for me.
Try pressing control and scrolling backwards.
No, on the live stream.
Yeah.
Check the live
Have
stream.
you been into the bug collection?
Or someone
It's
get
so
in.
hot.
Oh,
Yeah, when I was an undergrad,
Collaborate.
4 or 5 hours.
Got one concurrent viewer. Don't know who
It's
it
in the
is.
storage meeting.
Like that little conference room.
Can you see
We
it?
have all the crap.
Or is it just like I don't like? It's almost like it's zoomed in just that far.
I'm the only one in the room that puts this.
Oh no, not collaborate on YouTube.
Oh, it's like a double board.
Yeah, I don't know.
It smells horrible. It's also so hot. It's exactly what it is.
Oh, it is?
No, I didn't mess with
Yeah,
one of
well,
those
the bug
ones.
collection is in a like little janitorial closet.
It's working.
The actual storage room itself is changed.
Yeah.
Is it? It's not like zoomed in or anything.
So it's like a subset.
Oh, okay, yeah. So my screen is just like.
Try right in the YouTube data frame. There might be a zoom function there you can do. No?
Now you can see what I have on my end. This is the live stream.
Also, that's weird.
So that should be what I see, but I don't see it. Yeah, that's the show. It looks okay. I guess we'll
Yeah,
go
it looks
there.
normal.
I was always so scared that that I would make a change of clothes.
Yeah, there's a lot of cool
Close
stuff.
in the trash bag. Because I was like, I don't want to be the person.
No.
Yeah.
This is the second one.
All right, well I guess it'll work. Whatever.
You can't get it going right.
We'll go to senior grad and more grads for
So you got like like transfer.
That's what I thought too. That's what I told them.
Yeah, like a dice.
No.
I used to.
We were having trouble.
Yeah, it's in the store.
That's what I was trying to think of. I think it started with D. I was thinking back to but that was that big take one, right?
All right. All right, let's get going. My live stream screwed up. All right, so we got to finish early today, so I can go get this collaborate session. All right, so we did basic review of descriptive statistics. Really good, kind of get back into R. Review some of the functions. Some of you, it's like, here's the new functions. Here's how you do some of this stuff, and we're still going to be doing that because we're going to do statistical tests. We're going to review all of these one numeric variable tests. So our variable that we're going to work with now is either going to be continuous and discrete. We're going to go through the options of what we can do, some of the assumptions, what tests we can run, and so forth. All right, and each test kind of depends on what our overall goal is. All right, so tests that we can look at are basically 3 main types. One is a test of location. That's saying where our central tendency is. Are we comparing means? Are we testing if the mean is equal to some number? Are we testing if the median is equal to some number, and so forth? All right, we can also do a test of scale, which is basically tests of variance. How much our tests vary. Now, on a one sample test, or one variable test, we don't normally do that. We can, but generally we don't do that. Normally our tests of variance or tests of scale come into play when we start running like ANOVA, where we have this assumption that our variances are equal. We have to check that. All right. And then the third one is testing a fit to a distribution. So it's kind of like a combination of these two, both the location and the scale, because our distribution, our probability distributions themselves will define what the central tendency is and what the variability will be. All right, so in terms of what types of tests can we run, well, there is a Shapiro test that will test a distribution, but we're going to use QQ plots. Just tend to be a little bit easier, less susceptible to errors of sample size and so forth. All right, we can also do goodness of fit tests. We're going to learn how to do those when we switch to categorical data, categorical variables. All right. So figures and displays. Generally speaking, when you work with the data, you're going to present some sort of display that gives a nice, concise summary of the data. Sometimes you can use the displays to avoid having to report the mean and standard error in the paper, in the presentation, and whatnot. All right. If we try to do that, then we really only have one figure or display option, and that's going to be a histogram. Now, this is if we have continuous variables. All right, and we've already kind of introduced the histogram. Here's a full introduction. So our histogram is going to be the preferred method. The function is hist, all right, where we give it a numeric vector. And that numeric vector may be in a data frame, so you may have to use this data $ variable name to access it. We can give the breaks, which is the suggested number of bins in the histogram. All right, and we could also give it a vector ourselves. Like we can actually say, these are the breakpoints that I want, and R will do its best to follow. And then frequency. Frequency equals T or frequency equals F. All right, so and we said, it kind of comes down to, do we want to plot the counts or do we want to do the probability density associated with that? That's for continuous variable. If we have a discrete variable, we could do a histogram, all right? But it's going to look a little strange because we have whole numbers. And usually that histogram then might place spaces between the individual bars, which is kind of what we want, but it defeats the purpose of a histogram. Histogram showing the spread of our data, the bars should be touching, all right? And when they touch, they imply that you have this continuous type variable. So if you have a discrete variable, I think probably the preferred method is going to be a frequency table, which is going to report the counts for each of the values in our data sets. Now, this is going to work if we're doing like males in a clutch, where your clutch size might only be 7 or 8, so your table is going to have 7 or 8 rows. But if you're doing, total seeds produced by a plant where your seeds range from 100 to 1,000, that table is going to be massive. All right, you're going to print out your thesis and it'll be, 1,000 pages where half of that is just a table. All right, so in that case, with something that large, it might just be better to use a histogram or to avoid the diagrams or the figures themselves and report means and standard error. So if we choose a table, how do we make it? Easy function table. Just table, and then we give it our vector that we want a table of, and it will tabulate our counts for us. So this is great. If how many sample sites did you have, Matt, where you collected your skunks?
Ooh, like 274.
Different sample sites?
Yeah, different daytime nesting places.
Okay, and then of those nesting places, they were in like different ecotypes or different ranges?
Not all the time. But yes.
Were they all in one?
No, they weren't all.
How many private properties or how many properties did you sample?
Just one property.
That's
I'm not giving you the answers you want. I'm sorry.
Blake, how many fish did you? 113 fish. How many lakes did you sample at?
4.
All right, 4. So in his data set, he'll have one column that has the lake with each lake, and each row represents a single fish. So if I ask Blake, hey, how many fish did you have in each lake? What would you do? Probably go to Excel and start counting up each row, right? Or highlight it and get the count. Well, you can just do a table of your lake, and it would count. It would say how many different lakes do we have, and how many of them are there in your data set. It produces a frequency table. Very, very useful. Very useful. All right, so here's some practice figures and display practice. All right, it's in the Scoville data set, scoville.csv, posted on Blackboard. Download it. As you download it, I'll just describe it. The idea is that you grew 200 jalapeno plants, harvested the peppers. All right, so for each of these plants, you collected their peppers and pooled them to kind of get an average for each of the individual plants. All right. Now, as part of this, you know how many peppers were collected for each plant, that's your count, and then you calculated the average skin thickness of the peppers. So using all the peppers, you know the average skin thickness for the plant, as well as the average Scoville unit. What's a Scoville unit? It's a measure of hotness, right? Heat, measure of heat, hotness. All right, so download the data set. All right, we want to make an appropriate figure display for each of our 3 variables in that data set. So go ahead and try to make it. Let me open up our studio. And just to kind of get you started, again, we're on a new presentation. So we finished off the basic stats. What I would likely do is create a new file, new markdown document. Create a new markdown document and then start from there. So I have my data sets. I would have my functions if I needed, and any libraries. So that way you can create your different chunks. They're ready to go, and you know that if you were ran into doing a t-test and you say, I can't remember how to exactly do it in R, you can easily go back to this markdown document. Don't know if I downloaded it. What you call your data set? You can read it in. Make it a phone call?
Yeah, I just super pro and like your middle name is Statistics. Oh,
Or did it have like
Yeah, this is the line. I'll show you. This is. Yeah. It doesn't look good. I feel like the frequency table is tiny. That's not how the frequency table template looks. It doesn't matter. There's nothing.
Yeah, it grows the same size as everyone else.
No, mine's tiny.
Yeah.
It's only got like 30 entries. And not the size of the table, it's the data that I'm
Any issues or problems right now? I grabbed my data set. Imported the data set. Copy and pasted. So, got it. That way when I save and open it, it's there. It's good to go. Then I ask you proper displays. So what did you do for count? So here's a table of count down here. And I'd ask you, yeah, it's discrete, that's our preferred method, but how many different values do we have?
10 or 11-ish.
Well, I figured there's like.
Same numbers?
There's an 11 there.
Because it goes to 11.
1 to 11.
So there was two plants that had 4 peppers with it.
Oh.
One plant that had 7 peppers, one that had 14, one that had 15, one that had 17, one that had 20, 4 that had 21, and so forth. So the number of different categories that we had ranged from 4 up to 65. That's how many we had. Now we can count them up. Right? Count them up, but I can see right like that. I'm going to have a hard time presenting this as a table format. So just looking at that then, I could say, yeah, maybe the table isn't the proper way to do it. I think a histogram looks a whole lot better. Histogram, the bars touch and implies that we have a continuous variable, but if we're looking at how much variation is there in the total number of peppers produced by each plant, I think this gives us a pretty decent idea. Shows that on average, I mean, our middle points are right here. We're looking at 30 to 40 peppers maybe on average produced by each plant. So I would lean more towards that history. Now, what about Scoville?
Histogram.
Definitely histogram. Again, even though the number is a whole number, you can say it's a discrete number. There's so many of them, there's no good way to present it as a table. You have a whole bunch of those values that it's only one. It only appears one time. Now you can kind of make a table by grouping them. So you could say Scoville unit between, let's say, 4,000 and 4,100. This is how many we had. 4,100 to 4,200. This is how many we had. That's basically what a histogram's relay. That sort of information. So I think this works. What about thickness?
Histogram.
Yeah, I think histogram works. And we could adjust them if we wanted to. Change the axis labels and stuff. That could be for another time. All right, so we made those figures and displays, and that's always going to be one thing that we try to do. Try to look at it just to see what happens, because what if we mistyped something. So here's thickness, right? From 0.1 up to 0.6. What if there was a mistake? So you don't need to copy this. What if the very first item was 0.6, but you actually typed 6 point and then hit enter? And you didn't catch that. And let's say that this wasn't the first one. This was buried into our data set. Okay, maybe the 121st row. You wouldn't know it's there. You'd calculate an average. You'd report the average. You'd have the variance. You'd do all of that stuff, all the summary statistics. Everything's looking great. And then you do a histogram. Because committee member says, well, did you look at the data yet? No. Go look at it. And you get a histogram like this. That's a problem. This is going to very quickly show you that, hey, I've got some odd number in my data set. Let's go look at it, see what it is, see what the problem was, and fix it before I start testing for means, testing for variances, and all that other stuff. So there's a reason why we look at these displays first. Big part of it, try to catch those mistakes in data entry. I've done it. Blake's done it. Right? But that was a little bit harder to find because it could have still been in the range, right? It's a good thing you kept your data files. All right, so, and I did it in snails. So millimeters with 2 decimal places. Yeah, there were some where it ended up decimal place got moved over. I forgot it, and I had like 100 millimeter snail. But it's just not even possible.
Big snail.
Yeah, freshwater snail.
Yeah.
All right, so tests of scale. This is the variances, and this is pretty uncommon for one continuous variance, for one continuous variable. If we are going to do a test of scale, all right, what are we testing? We're testing variability. When might we do this? If you're doing some sort of morphological study, comparison to a species description, and you want to see if your sample of unknown species, your unknown snail species, all right, if that variance equals the published variance, so you're comparing your sample to a published value, that's when we might use it. How common is it? Pretty uncommon, because most of those morphological papers, at least historically, they didn't give the variances, they gave ranges instead. All right. If we did want to do it, what are we testing? Well, we assume that our sample came from that population. So we assume that our sample variance, S squared, equals that population variance, sigma squared. That's our null hypothesis. That's what we're going to check. We're going to see how likely is it that our sample variance actually came from that population if this is true. Our alternate hypothesis then is that it's not equal, or our variance is larger, or our variance is small. We can do two-tailed tests, or one-tailed tests with this. Classical tests do exist, all right? But we don't really learn how to do them because, again, this is just kind of too uncommon. It's a specialty area. You know, it's a specialty test that, you know, most people are never going to use. So I don't teach it. The other way is, instead of doing that test, we could do bootstrapping. Now, we did the bootstrap mean, and we wrote a function for that. We could easily adjust it to do a bootstrap variance to get a 95% confidence interval of our variance value. Again, it's going to be the similar procedure, or it's going to be a similar code. We would just have to modify it. So instead of calculating the mean, it's doing the variance and saving the variance and doing the quantiles of that. Now, again, since we rarely test variance, we're not going to do it here, but I wanted to present it just in case you ever encounter a one sample variance test. And of the classical tests, I would say the bootstrap confidence interval is probably better. It's probably the best out of all. The other thing is testing fit to a distribution. All right? We're going to do this. We're going to do it a couple times, a couple different ways. We present this because many important biological processes are defined by a probability distribution. All right? Your sex ratios and clutch sizes. That is a probability distribution. So you go out and collect, 100 different nests. You can fit your sex ratios to this binomial distribution, no problem. Spatial patterns, survivals, time to death events. Those follow a clearly defined probability distribution. There are other things though, like infection intensities in parasite work. How many parasites are in individual hosts? That follows a probability distribution. And in a lot of cases, we want to know, does our parasite, does our sample follow that distribution? Is it what's known, or is it different? And if it is different, that's kind of interesting in and of itself. What out there is causing this change, causing this deviation from a known probability distribution? Now, we can fit distributions, we can fit continuous distributions, and we can fit discrete variables. Now, if we have a discrete variable, typically what we're going to do is do a goodness of fit test. So we're going to test if our variable of interest, what we've measured, let's say sex ratio, number of males in a clutch. We're going to test if it's actually random. And by doing that, we're testing it, does it follow this probability distribution? Because if it is randomly generated, then it follows that binomial distribution in our case. All right, we're going to learn how to do this. And there's actually a package that's pretty good at doing these goodness of fit tests and fitting these various discrete distributions. What about continuous variables, though? We don't use goodness of fit tests for those because it's basically, we have infinite number of possibilities between our extremes. So we can't really have the probability of getting, a measurement of 2.1 because it could be fractions of a millimeter either way. All right. So goodness of fit tests don't really apply to that, but we can do some other things. All right. The most likely case for us is testing if our variable follows a normal distribution. And the reason why this is important is normality of our variable is assumed for several classical tests. ANOVA makes that assumption. T-tests make that assumption. All right. So we're going to have to know how to test for normality before we can proceed with these classical tests. There's two different ways to do it. One is the Shapiro test. This is a statistical test. We'll get a test statistic, we'll get a p-value. But as I have this in capital letters, this is not preferred. Why is Shapiro not preferred? It is sensitive to sample size differences. Sample size is less than about 100. You can have a hard time detecting non-normality when it actually is non-normal. All right. Sample size is greater than about 300. It's going to detect the slightest deviations, which normally we can ignore with our classical tests. So Shapiro-Wilk test, I don't recommend it. The only time I say do it is if you have a committee member or a reviewer that says, I don't like anything where you have some subjective claim. I want to see p-values, in which case you're going to be forced to run Shapiro-Wilk test. Preferred method is this quantile plots. Yes, it's a graphical assessment. Yes, it's subjective. But that's okay because most of the tests that we run, they're going to be robust against this normality violation. So if we're not precise, if we say, well, it may be normal, it might not be normal, that's normally an indication that our test is going to do just fine. All right, so that's why these graphical assessments are okay. But if we arrange Shapiro-Wilk and it says p is less than 0.05, you're going to be stuck and saying, well, now I can't do a t-test. What else can I do? We don't want to do that. So if you're forced to do a Shapiro-Wilk test, how do we do it? Just like this. All right, so Shapiro-Wilk test is a test of normality. Our null hypothesis is that our variable, x, capital X, our variable, is normally distributed and it has some defined mean, a defined mean and a variance. And I use sample here to emphasize that it's our sample variable is a normally distributed defined by its mean and standard deviation. Our alternate is that it's not normal. Okay? This is one of those tests where it's not like we can't say, is it more normal, is it less normal? It's just it's either normally distributed or it's not normally distributed. We access it with the Shapiro.test function. This is a built-in function in R. For this function, we give it a numeric vector. All right, we give it a numeric vector. That vector might be in your data frame. So you may have to use the data $ variable name format to pass that to Shapiro.test. As I said, this is sensitive to sample sizes. Right? Lacks power at smaller sample sizes. Smaller sample sizes is like 100. I can pull open a script. I've done this before where I made data sets that were clearly non-normal, drawn from a non-normal distribution. And on those, at like, if we have a sample size of I think 75 or 80, Shapiro-Wilk detected non-normality in only about 30 or 40% of them. So it really isn't, it's just avoided. And that's why I said do not use unless a reviewer requires p-values. And our sample sizes is between this number. If it's not, then I would just respond to the reviewer and say, look, Shapiro-Wilk lacks the power, not enough power, or look, our test is robust to violations. We really don't need to do this. And your associate editor should recognize that you gave a valid argument. Or they'll go to the stats person and ask them. All right, what about a quantile plot? This is also pretty easy to do, but it's a graphical assessment. Now, this doesn't just fit normal distributions. We can fit any distribution that's built into R. So if we wanted to compare our t statistic to a theoretical t distribution, we can do it. If we do, let's say, a permutational ANOVA, where we've generated a null distribution of F statistics, and we want to see, did our F statistic follow the theoretical F distribution? We could do it. All right. Now, normally though, we're going to compare our variable to test it for normality. So our null hypothesis for this assessment, it's assessment, not test, is that our variable is normally distributed, defined by our mean and standard deviation. Our alternate is that it's not normal. So we're going to use the car package. All right, so you're going to have to load up the car package. How do we load it up? Yep, so definitely you can go to the packages and just, I can't even. So I could go right to the package and find the car and click it. But when I click it, the code will appear right down here. And we need that code so when we save and open this markdown package, it'll run it when we need it to run. So the function is library and then the name. And that says, okay, load the library into memory. So I'm going to load that car package so that we have it. So it's loaded. Now, how do we do it? QQplot, note the capital P. Note the capital P. We give it our numeric vector. And again, it may be in the data $ variable name format. And then we can give it the distribution. Distribution equals whatever distribution we're trying to fit. Norm, or normality, or normal distribution, is the default. So you don't have to actually tell it distribution. You could just do QQplot, our variable name, or QQplot data $x, or data frame $ variable name. So all right. All right, how do we assess it? So you're going to see with our practice. This QQplot makes a plot that is fitting our observed to predicted. What's observed versus predicted? Our observed quantiles of our data set. So 5th quantile, 10th quantile, 20th quantile, and so forth. 30th percentile, 50th. The medians of 50th are quartiles, or 25th and 75th quantiles, and so forth. We're comparing our observed to what would be predicted from a normal distribution. So using the same mean and standard deviation of our data, we can predict where each of our quantiles should fall. If we're normally distributed, then our observed will match what's predicted, and all of our points will fall on a one-to-one line. So whatever we predict, so for this x value, we predict that to be at that quantile, and that's exactly where we saw it in our data set. So if we're normally distributed, we follow this one-to-one line. If we're not normally distributed, then you'll get something that deviates from this one-to-one line. It could be, I'm going to leave the one-to-one line up there to kind of show examples. It could be something like this. All of our points look something like this, where our observed quantiles increase much faster than what our predicted would say. This is an indication of skew. Or we have something like this, where our predicted increase much faster than what we actually observed. That's another indication of skew. Or you have something that is a little bit more complex. In all of these, we no longer follow a one-to-one line. We're not following a straight line. We're curved in some way. All right? So when we look at this, we're looking for, does our points fall on this one-to-one line? There's our one-to-one line. But you're going to see that our points, it's random. It's a random sample. Ideally, they all fall on the one-to-one line, but we're going to get some variation. So how much leeway do we give our data points? Well, this is a nice part about the CAR package. The CAR package actually places 95% confidence envelope on our graph. This is a CE. So confidence interval is just like on one axis. Confidence envelope kind of covers both those axes. Our rule of thumb will be that nearly all of our points should fall within that confidence envelope. Right? And we know we're not going to line up exactly on the line. But we're going to say, as long as most of our points fall inside this envelope, we're going to be good. All right? There are some exceptions. We can allow some of our extreme points to fall outside of our lines because our extreme ends, those are the ones that have a small probability of occurring. It's not a zero probability. There is a small probability that we could see something like that. So we're going to allow some of our points at the extremes to fall outside that confidence envelope. And that's why that envelope kind of flares out on both sides. How much is too much? Maybe 5, maybe 10%. Kind of depends on our sample size. Normally, if things look off, you're going to notice the curvature of your data points. All right? You're going to notice the curvature of the data points, and we're going to be seeing some of these. It's kind of hard. I'm doing my best to kind of give you these generalizations, but the more data points that you work with, the more data sets that you work with, you'll start to get a feel for, oh yeah, this one's obviously not normal. This one's got some problems I have to work with. All right? So here's some practice. We're going to work with Scoville data set. All right? And what we're going to do is we're going to assess normality of count using the Shapiro Test. We're going to do it one time so you can see the output, we can see the test statistic, you can see the p-value, we'll make our conclusion. And then we're going to assess normality of the variable Scoville and thickness using the QQ plots. What I want you to do is do the assessment and then write your interpretation as if you were including it in a scientific paper. That means remember those things that you may need to include. Your test statistic, degrees of freedom, p-value, and your conclusion interpretation. How's it going?
Good.
Did you finish them? Still working?
Right.
Okay. We're gonna just review this output and we'll be done. All right, you ready? All right, so kind of added some stuff. Shapiro Test. Again, emphasize that it's not the preferred or recommended method to assess normality, but if we need to do it, we use Shapiro.test. So we get this output. Real nice output, tells us what test we ran. Shapiro normality test. It gave us a W, gave us a p-value. So what do you think W is? That's our test statistic. What do you think p-value is? P-value.
P-value.
All right, what's our conclusion?
No.
It is normally distributed. Remember what our null hypothesis is for this test. It's that our data is normally distributed. All right. This gave us a p-value and said that just from a random sample, we've got a 16% chance of getting data as extreme or more extreme. So as what we saw or worse than what we saw. So that's not enough to conclude that it's not normally distributed. So yeah, this is normal. right? Write up, pepper count appears to be normally distributed. Shapiro Wilk, that was our test that we ran. I gave the test statistic. Note the 3 decimal places. This is one of those exceptions where we report 3 decimal places. Because what happens if we have a W of 0.996? It rounds to 1. We wouldn't give it. What the W is, it's scaled to 1. The highest it can be is 1. The farther away you are from 1, the less likely it is that you're normal. Or I should say, the more non-normal you become, the farther from 1. All right? And I gave a p-value, 0.16. 2 decimal places because we're above 0.05. Where's the degrees of freedom? What's that? There isn't any. R didn't give us a degree of freedom, so we don't report it. We don't report it. All right, quantile plots. Scoville. Here's my plot. So I say this is normally distributed. Our points fall pretty close to the line. Some fluctuation. We can note this spot here. Now, what's important with the graphics is that it's the center of the point. Not like any part of the point. It's the center of the point. That's what matters. So even though some of our circles, I could change the size to make these smaller. And then they would all fall under this envelope. So yeah, everything follows a straight line. Yeah, there's deviation. That's just randomness. That's stochasticity. So I would conclude that Scoville units is normally distributed. And my write-up is as simple as saying quantile plots suggest Scoville units is normally distributed, or average Scoville units per plane is normally distributed. You told the reader that you use quantile plots in your assessment. What about thickness?
I have a question real quick.
Yeah.
So would you include the quantile plots as a figure, or like if you're, say, trying to submit to a journal, or would you just include it in the,
If they ask for it.
if they ask for it?
Yep, if they ask for it. I've never had anyone ask for a quantile plot.
I was just.
All right. You say non-normal. Why do you say that?
Kind of coming out of the line.
Where at?
Bottom.
Okay.
Like towards the middle, if you look towards the middle.
Oh, over here.
Black line right there.
Yeah. So this could be a tough one. Yeah, we allow some extreme points. That's kind of a lot of extreme points. You started like that point might be in, but then we jumped right back out again, right? And we've got a point out here. But pay attention to this middle. Man, it really does look like some of these points are out. If you're out in the middle, that's a bad sign. You're not normally distributed. So on this, yeah, I'd err on the side of caution and say this is probably non-normal. And I'd probably conclude, just like it did, it suggests skin thickness is not normally distributed. And you can see it in our histogram. Rerun that. There it is. You can see it. We do look skewed. Now, is this skewed enough to affect a t-test or an ANOVA? Maybe. Maybe not. That's why ANOVA is so good. Is that even if this is skewed and it looks like it's slightly non-normal, ANOVA is going to be robust against those violations. Now, in this, I'd probably say, okay, we're going to run Fligner-Colleen and non-parametric test for equal variance. If that test of equal variance says that they are equal, then I think ANOVA is probably going to be okay. But if you have any doubt, just to go with non-normality and don't do the ANOVA, do something else. All right? All right. Make sure you save it because we'll keep adding on to this script. All right, so we have the assessments. I did this in a specific order because our t-test requires this normality assumption. And a t-test is one of those one sample tests that we're going to be checking. All right, so what we will do is move to our tested location, talk about Z and T tests, learn how to interpret our bootstrap confidence intervals, and so forth. And then I have some practice problem that we can kind of practice doing these just to kind of get back into the field. And I have a homework problem that kind of gives you a repeated way to test and do your interpretation. In years past, it wasn't necessarily running the test that causes people problems, it's the interpretation. Memorize your null hypothesis. Know what what every single null hypothesis is for the test, because that's what our p-value then tells us what to do. Either we accept that null hypothesis or we reject our null hypothesis. You have that down, memorized, then your interpretation should go well. All right. I think we will stop here.
So what I was talking about for the journal was the functions that they sometimes ask for in R.
Oh, sometimes. No,
Do you include?
no. You can do R, and you can say it's part of your method to check something. Normality was assessed using the car package. Quantile, in the car package. And you may need to cite the car package. That is, it tells you how to cite the car package.
I know ASM wanting people to include markdown. With their submission, I guess.